Hello, and welcome to another Wolfram R&D live stream. My name's Ian Ford. I'm a research staff member at Wolfram Research, and today I am excited to be talking about tree representation for XML, JSON, and symbolic expressions. Brief outline of the talk. By the end of this talk, you will know how to represent all kinds of different trees using the Wolfram trees functionality, and also how to construct trees of a variety of different structures. Next, I'll talk about different visualization options and functionality that's available. Then I'll get into some of the basic properties and measurements that are available for trees, and finally with computations that can be performed on trees. So first, some terminology. Trees are fundamental data structures in mathematics and science that are used to represent hierarchies and nested structures. So let's look at some examples of that. Here's an example of a couple sentences of text, and we see the overall sentence structure. Here's the first sentence, the second sentence, then each sentence is composed of nested text elements that are tagged with their part of speech. So you can see verb phrase, noun phrase, and punctuation are all nested within this sentence. And similarly, this sentence has a noun phrase, a verb phrase, and punctuation. So that's one example of trees, is structured grammatical text. Another example of trees is geological periods. So here we see on the left the Phanerozoic period and all of its subdivisions. So on the vertical axis, we have the number of millions of years ago. So the height of the rectangles is the number of millions of years that those periods lasted. And then as you go horizontally, you can see the different subdivisions of all of the different periods. Another important example is XML. This is a structured text format for representing tree data. So here we see an XML document. It consists of a collection of opening and closing tags. So here we have a paintings tag and a closing paintings tag. Then everything between those two tags is an XML element, and XML elements are hierarchical. So within the paintings tag, we have these multiple sale elements representing sales of different famous paintings, and within those, different elements representing different properties of that sale. So how can we actually represent these things using the Wolfram trees functionality? The primary construct here is this symbol tree. So tree represents rooted, ordered trees with leaves. So to see what this looks like, here we have a tree with 3 leaves, which are the numbers 1, 2, and 3. So if we evaluate this example, we see we get a tree with 3 leaves, 1, 2, and 3. Another feature of trees is that you can have data not only in the leaf nodes, but in every node. And the way that is done is by using an optional first argument. So this is a tree with the same 3 leaves as children, but the root node will contain the number 0. So if I evaluate this, here we get this new tree. You see the same 3 leaves, but now the root node contains the number 0. The way that you construct hierarchies using trees is just by using trees as children in the second argument. So here we have 2 trees. We can see what these trees look like by evaluating this in place. So here we have a tree with 2 children. which are themselves trees. And again, we specify a piece of data for the root node. So when we evaluate this, here we get this tree. You see the 2 children and the root node. In version 13.1, this was extended so that you can also name the branches for trees, which is important for several applications. So here's an example of a tree, again, with the same 3 leaves, 1, 2, and 3. But this time we use an association rather than a list and supply keys for each of the children. So the leaf 1 will have the key A, 2 will have the key B, and so on. So when we evaluate this, here we get a tree, and you can see the keys A, B, and C are used by default as the edge labels. Now this is incorporated into all of the trees functionality, in particular, all of the functions that construct trees and all of the functions that operate on trees also support this association syntax. So here's a function we'll see a little bit more of later, nest tree, that can be used to construct trees. And here I'm constructing a tree where the branches are named even and odd. So we evaluate this. You see here is this tree, 3 levels, and the branches are named by the strings even and odd. Like I mentioned, you can use the associations in all of the trees processing functionality. So here's an example of replacing a subtree by specifying the name for the branch that you want to replace. So if I evaluate this tree in place, you see we've got a tree with keys A and B, and we want to replace the second one, the one with key B, with a new value. So when we do this, we'll get a tree where 2 has been replaced by the symbol XX, and there we see it. B now has a new subtree specified by tree replace part. So that's how to represent trees in general. Let's look at some concrete examples of different kinds of representations that can be done. Probably the most important is Wolfram language expressions. So of course, everything in the Wolfram language is represented as an expression. Here we can see an example. This is a computation today plus 1 day that somehow symbolically represents tomorrow. We evaluate that. We get this date object for tomorrow, right? So let's look at what's going on underneath this. So this expression, this date object, since it's an expression, has the form some expression x per 0 called the head, and then 0 or more expressions, x per 1, x per 2, and so on, that are called the arguments. So if we use the function full form, we can see what any expression's full form looks like. So let's take the full form of this date object, and here we see this nested expression structure. The head is the symbol date object. The first argument is a list encoding the day, and the second argument is a string for the granularity. Now, this is a nested structure, so we can convert it into a Wolfram language tree, and the way we do that is by using the function expression tree. So if we take expression tree of this date object and specify that the structure that we want is the heads of the expression, we evaluate this, and here we get this tree. So just like the head was a symbol date object, here we have a tree where the root node is the symbol date object, has 2 children, the first children corresponding to the list, and the second child is this leaf corresponding to the granularity. I said that today plus 1 day is also a symbolic expression. It happens to be a symbolic expression that evaluates to another expression, but we can also look at what the full form of the original expression is without evaluation. So here I'm taking the full form of today plus 1 day and wrapping it with unevaluated to prevent premature evaluation. Evaluate this, and we see the expression has head plus 2 arguments, the symbol today, and a quantity of 1 days. So just like we could do full form, we can also do expression tree. Now, rather than specifying heads, I'm going to say held heads so that things like the symbol today don't evaluate, and we can see what this tree looks like. And very similar here, the head was plus, so the root node of the tree is symbol plus, and has 2 children, today, and a quantity of 1 days. So that's a nice thing, that you can construct trees out of Wolfram language expressions, and you can do so both with and without evaluation. However, that's not the only way to construct a tree from an expression. So here you could see the kind of the first way of constructing a tree was to take the head of the expression and use that as the data, then use the arguments as the children. Another way is to treat the head and the arguments of the expression equally in some sense. So here the head, x bar 0, will be the first child rather than the data, and then the arguments will be the remaining children. So since we're including a subtree for the head, we specify the option heads goes to true, and I'm specifying the structure held atoms so that we can see just the atoms that appear in this tree. Evaluate this, and there we see a very similar looking tree, except now we have just the leaves are labeled, and they include all of the symbols in the entire expression, including the heads. So heads and atoms and their held versions are 2 ways of constructing trees out of expressions, but there are many more. So here's a table kind of showing these 4 heads, sub-expressions, atoms, and null, both with heads goes to false and true. So if we look at this, we can see this grid of all the different ways that an expression could be converted to trees. And these are all important for different purposes. So some of them, for example, preserve the level specifications. By that, I mean the levels in the expression line up with the levels in the tree. And some other ones preserve the position specs. So the position in the expression will correspond with the position in the tree. So that's arbitrary expressions. We also have built-in rules for converting more specific types of trees into expressions. So one type that's particularly important is XML. So you can import XML strings or files into the Wolfram language, and they get represented as symbolic XML objects and elements. So here we can see an example of that. So we see the entire document is an expression with head XML object document, and then it has subtrees. There's this XML object here for the document type declaration and the encoding, and then lots of nested XML elements that correspond to the tags in the XML document. So we can convert this expression into a tree using the specification given by the used to be called the document object model, or the DOM. So we take this expression, convert it to a tree, and specify that we want to use the structure of XML. You can see what that looks like. So this is yet a different way of constructing a tree from an expression, where now the nodes correspond not just with the heads and the arguments of the underlying expression, but with the actual nodes that appear in the DOM. So here we have The root node is the entire XML document. Then we have the body, which is this paintings element and all the different sales. And you can see the elements with all of the data about the sales. Another very common representation for trees is JSON. So JSON is primarily two things. They call them objects and arrays. Objects have key value pairs and arrays are basically lists. So let's look at an example of a JSON object. So here's what this string would look like without backslashes for the quotes. This is some kind of a tree representing properties of few different chemical elements. You can import that string into the Wolfram language as nested rules using the JSON import format. So if we import this string, we see this representation of the keys and values as lists of rules, where the left-hand sides are the keys and the right-hand sides are values, which can themselves be nested objects. We can convert that representation into a tree as well using expression tree. This time you have to specify the structure JSON. So if we do that, get this tree where we have unlabeled nodes for the objects, and then the children are represented as a node containing the key, and then a single child containing the value. So these keys have a single child, which is itself another JSON object, whereas these keys down here have a single value, which is numbers and strings. This isn't the only way that JSON can be imported into the Wolfram language. You can also represent JSON using nested associations if you are willing to have unique keys. So here, if we import this JSON string using the import format raw JSON, we'll get nested associations. So very similar, except now we have an association where the keys of the association are the keys of the JSON object, and the values are represented with associations. So if we convert this to an expression tree, we want to use the structure raw JSON, same as the import format. So when we convert this to a tree, we now have a slightly different representation, where now all of the objects are, again, unlabeled nodes, but rather than having additional nodes for the keys just become keys in the tree, which display by default as the edge labels. Just want to point out for JSON that both JSON and raw JSON support arbitrary JSON expressions, which can be a mixture of objects and arrays. So this is just an example of that, and I'm going to import it both as JSON and raw JSON and convert it to a tree. See what that looks like. So there we can see objects are these things that have a key and a value, and the two different ways of representing that. And then arrays are just ordinary lists. So this is an array, and arrays are represented the same for both JSON and raw JSON. Another very interesting example is constructive solid geometry. So it's called a CSG region, can be constructed using nested combinations of operations like union, intersection, and difference, where the leaves are given by solid regions. So here we have a CSG region that's the difference of two regions. The first is itself the intersection of a ball and a cube, and the second is this cylinder. So we evaluate this. There we see the CSG region. You can kind of see that it's the intersection of a ball and a cube within a cylinder differenced out through the middle. We can convert any CSG region into a tree using the function CSG region tree. So if we just then take this CSG region and do CSG region tree to it, we get the constituent tree where the leaves are these solid regions and the inner nodes are these operations of intersection and difference. So those were just a few examples of constructing trees using built-in rules, using expression tree and CSG region tree. There is also the ability to construct trees using custom rules, user-supplied rules. And the primary way of doing that is using the function nest tree. So here we are using nest tree. The initial value or the seed value is going to be just the symbol X. And here we have some operation that returns a list of children. And we're saying we want to apply that operation to give a tree of depth 2. So we evaluate this. There we see a tree with level 1, level 2, and at each level, the operation given to nest tree is applied to the leaves to get the next level. So this can be used to construct completely arbitrary tree structures from any initial expression using any functions you want to compute the children and the data. So one example of that using databases, here we have the initial entity is, or the initial expression is going to be an entity. So in this case, Queen Elizabeth II, and the function is going to be a entity value lookup that looks up in the Wolfram knowledge base what the children of that person are. And we're again going to do 2 levels. So we evaluate this. Hopefully it doesn't take too long. Great. There we have Queen Elizabeth and 2 levels of her descendants. Another example similar to this of computing the children of a tree. You can also specify a optional argument to give the data for the nodes. So here I'm going to start with my user base directory. The children are going to be given by the files within that directory, and the data is going to be given by the base name of those files. So I'll evaluate that. Here we see a tree representing the first couple of levels in my user base directory. Now there's a question from chat. Given that JSON and XML can also be mapped to nested associations, can you compare trees versus association, say lookup speed and other features? Yeah, so I'll get to lookup a little bit later. Trees right now still has quite a bit of performance that's being left on the table that we're interested in speeding up. So yeah, I think I'll get to that later. For visualization, now we've added in version 13.0 options to control some of the aspects of the labeling and styling for trees. So here I have a tree with 2 elements. I want to label the first one with the string 1, and here tree element style is specifying that I want the second child to be a light red color. So I'll evaluate this. We get a tree where the first child has this label specified and the second child has that style specified. Now in version 13.1, we added detailed control for every aspect of labeling and styling for both nodes and edges. So here's an example that kind of showcases all of that together. We're going to look at all of the possible values that can be used for the node shapes. These are the same as the settings that are supported by vertex shape option for graphs. So we say tree element shape function, and we're going to use each shape for a different node. There's also new options that can compute styles and labels from the data. So for example, parent edge style function, I'm saying for all nodes, I want to compute the style by taking a hue computed from the data. So this is the data, divide it by 100, convert it to a hue. Similar for, and that was for the parent edge styles. So that'll be for the edges. For nodes, there's tree element style function. This time I'm going to have the style depend on not just the data, but also the position of the node in the tree. So the left-hand side here is a pattern that matches a position in the tree. So the node style is going to be computed by taking the data and dividing by basically the length of the position, which gives, as you go down into deeper levels of the tree, the length of the positions get longer. So this denominator will be larger the deeper we go in the tree. And finally, an example of generating labels using tree element label function. I'm just going to use Roman numerals for all the labels. So putting this all together, let's see what that looks like. Right. So here we have a tree. You can see the variety of different shape functions that are available. And you can also see the node and edge styles have been computed from the data and the position, and we're using Roman numerals for the labels. Another function that was added in 13.1 is unlabeled tree, and unlabeled tree can be used to basically strip out all of the labeling and styling options and suppress any labels that would be there so that you could just see the overall structure of the tree. So here we have a random tree of 100 nodes, and we've applied unlabeled tree to it to get just this kind of a view. Version 13.1 also added options for specifying tree layouts. So one simple thing you can do with it is to just specify an orientation for the root vertex. So in this example, I'm using the function random tree again, and specifying tree layout goes to right. So now rather than the root node being at the top of the tree, the tree is going to be rotated so that the root node is on the right. So we evaluate this. There we see this tree, the root node is on the right and the branches move to the left. Tree layout also supports named embeddings. Again, and these are some of the same embeddings that are used by the option graph layout for graphs. So if we specify tree layout goes to radial embedding, there we get a tree with the root node, and the children are now laid out radially. Similar to how in graph you can specify graph layout or specify the vertex coordinates manually. In trees, you could specify coordinates using the option tree element coordinates. So here I have a tree. The root node contains the number 0, and it has 2 children, which are the numbers 1 and 2. And we want the root node to be at the origin, the first child to be on the y-axis, and the second child to be on the x-axis. So we evaluate this. There we've got a tree with the specified coordinates for the nodes. Moving on, another feature that's really important for visualizing large trees is the ability to elide information. So by default, if a tree has more than 10 children, then the remaining children are elided. So we can see what this looks like by doing tree of, this is the list from 1 to 15. And we see the children 1 through 10 appear just fine. But then the remaining 5 nodes are elided, and we get this summary here that there were 15 total children for that node. In version 13.2, we have added a couple ways to control elision. Started adding ways to control elision with these 2 features. So first is this max displayed children option. So any tree or tree constructor, you can specify max displayed children, and that sets the default number of children to display. So this example now, if we say max displayed children goes to infinity, we will see all of the children, not just the first 10. There we go. We see all of the children 1 through 15. Now, if you want to globally set this to perhaps a smaller limit, you can set the global variable $max displayed children. So here I'm going to set the variable $max displayed children to 2 and generate a random tree with 1,000 nodes. Now, it'll only take a moment to generate a tree with 1,000 nodes, but by default, the visualization would not be very good because 1,000 nodes is a lot to cram into a small display. But with max displayed children goes to 2, that means that at every node, this tree will only display 2 children. So we should get this tree with 1,000 nodes, but we only have to see some of them in the visualization. So that can be very useful for working with large trees. Also, it's important if you set $max displayed children, remember to unset it if you don't want it to affect further things. So there I've unset $max displayed children. So that's kind of an overview of the different labeling and styling and elision options that are available. We also are interested in different kinds of visualization. So here's a different visualization from the automatic visualization as a graph that we've been seeing. So if I take this random tree, evaluate that in place, and we can see by default it formats as a tree graph. But if we do tree outline of that, we get a very different view where now the subtrees appear with openers. So here's the root node contains 6, and then there's openers we can click. So here's the first 4 children, and then we can continue clicking. We can multi-click and expand different subtrees, close subtrees again, etc. This is a another very useful way of displaying large trees when you don't want to see everything all at once. So here's the XML tree example from earlier. Let me reevaluate that. So there's that XML tree. Now to display that as an outline, I'm going to use tree outline, and here I'm specifying an initial position to be opened. So I do that, and there we see an XML, an outline of the XML tree with openers. And again, these openers can be closed and opened independently. So that's very nice. The way this works is that tree outline supports the labeling and styling options of the tree that you give it. So here I have a tree. It has edge labels and edge label styles specified. So when we do tree outline of it, we will get an outline where those labels and label styles have been respected. Evaluate that. And there we see the openers are labeled with the strings 1, 2, and 3, and the styles are given red, green, and blue. Another question, what does tree position of tree blank do? I will also get to that in a later slide. Moving on to basic properties and measurements that are available for trees. The simplest one is tree queue, which is just a simple function that returns true or false, depending on if the tree is valid or not. So here I have an expression, it's got head tree, but the second argument is not valid. This should be a list. So if I do tree queue of this tree, get false. Now, if I give a valid tree by using a list in the second argument and do tree queue of that, I get true. You can also see that it's a valid tree because if I evaluate this tree, it just stays tree of 1, 2 because it's invalid. If I evaluate this expression, it formats as a tree, right? Some other properties you can get from a tree. The data in the root node is accessed using the function tree data. So tree data of this tree will give the data in the root node, which in this case is the symbol A. So there I get A. Correspondingly, tree children gives the list of children in the second argument of tree. So here I have the tree, and it's going to have 3 children, the leaf B, and then these 2 subtrees with data C and E. So I evaluate tree children, and we get these 3 children. Another operation is to get the root node as a tree. So not just the data, but the actual root node with the children removed. So that's given by the function root tree. If I say root tree, I'm going to get this root node here containing A as a tree. So let's evaluate that. There we see we get just the root node A. Root node can also be given a level, and it will give all of the nodes of the tree, not just the root node, but all of the nodes from the root node down to that level. So if I say root tree with level 1 specified, that's going to give the root node with the children B, C, and E, but the children of C and E will be removed. So if I do root tree, we'll see that. And you see a tree with root node A, leaf B, and these 2 empty nodes, C and E. Negative levels are also supported. So negative levels count from the leaves of the tree up. So the leaves of the tree are given by level -1. So level -2 is going to be the immediate parents of the leaf nodes. So if I say root tree of this, should get a tree where all the leaves have been removed. And there we see a tree where the nodes A, C, E, and H remain, but all of the leaves B, D, F, G, and I have been removed. Another question, is it possible to change the shape of the edges, for example, width, similar to the edge shape function for graph? Yes, there is a function or an option, parent edge shape function. And I will not try to demonstrate that here, but it works pretty much the same way that the edge shape function for graph works. Some more basic properties is tree leaf queue. So tree queue tests whether a tree is a valid tree. Tree leaf queue checks whether a tree is a leaf. So here I have a tree with second argument none that represents a leaf. If I evaluate this in place, you see this tree with a single node, and notice that node has a square border on it. That's a cue that this is a leaf. So if I now do tree leaf queue on this, we get true. Now, any other tree, any other second argument other than none is not considered a leaf. So here we have a tree with root node containing data and 3 children. So since this has 3 children, it's not a leaf. If I evaluate that, you can see this is not a leaf node. So tree leaf Q gives false. Now, important thing to note is that not all single nodes are leaves. So here is a tree with a single node containing data, much like this, except the second argument is not none, it's an empty list. Now, if we evaluate this, you can see this is a tree with a single node, but there's a cue that it's not a leaf, which is that it has this rounded border, which you can see in other trees. Any node that's not a leaf by default has this rounded corners. So if I do tree leaf Q of this tree, it actually gives false because this is not considered a leaf. So there we see tree leaf Q gives false. So another helpful function to go with that is tree leaves. So tree leaves gives the list of leaves of a tree. So there we see the leaves, B, D, F, G, and I. Looking at chat again, are you not worried? Wolfram language is turning into Python with each dev team adding overlapping functionality, expressions, association trees, rather than cohesive orthogonal language. I'm not going to speak to Python, but I will say that we have a pretty unified design with the Wolfram language, and trees in particular. We have lots of design reviews with Stephen and with other teams to make sure that we do have a cohesive language and that everything kind of fits together well. But yes, that is a concern, and we work actively to make sure everything is cohesive. Moving on to measurements in trees. Here's a few. There's tree size, which gives the number of nodes in a tree. So here I have a tree. If I do tree size of this, I get 30, which these are numbered 1 to 30. So that checks out. Another similar way of counting kind of the size of a tree is to count not all the nodes, but just the leaf nodes. So if we do tree leaf count, that will give the number of leaves, which in this case is 14. Some other measurements are the depth. So if we say tree depth, that will give the maximum level of the tree. So we see the root node is at level 0, then level 1, level 2, 3, 4, 5, 6, and 7. So tree depth of this should give 7. There we get 7. The other thing tree depth can do is to look for a pattern in the tree. So see, there's this node here, 6. If I want to compute what level does that node appear on, you can give a second argument, which is a pattern. Here I'm just giving the literal number 6. So the number 6 appears on level 1, 2, 3, 4, 5. So tree depth should give 5. And there we see 5. Question from chat. Parent edge shape function is an odd name. I guess edge shape function could not be reused because its signature / arity is different. That's correct. So graphs, of course, so graphs can model trees, and there's lots of functions in the Wolfram language that give tree graphs. They do model things differently. So with graph, you have, let's look at an example. If I say tree graph, 1 goes to 2, 1 goes to 3. Right, so this is a tree graph. You know it's a graph because when you click it, it's got a purple border on it, right? So graphs are modeled using vertices and edges. So if I say vertex list of that. I get the vertices 1, 2, and 3. Let's say edge list. I get these edges. Now, one consequence of this is that everything is based on the vertex names that are given. So if I wanted to have this child have another node coming from it with label 1, let's see what that would do. So if I say 3 goes to 1, this might actually just not work. Doesn't work. Let's just do graph. Right. So in graph, the vertex names are unique. So here I've got a graph with an edge from 1 to 2 and an edge from 1 to 3. So then this edge from 3 to 1, this one is the same as this one. So you end up with a self loop, right? Whereas tree has a different way of modeling things as nested objects. So tree of 1, 2, 3. We look at that internally. There aren't vertices, there aren't edges, there's just nested tree objects. So that's one reason why the visualization options for tree are different, is because of the need to support these nested structures. The other thing is trees, the primary thing that they have is data in the nodes. And importantly, the data, unlike a vertex name, does not need to be unique. So if I want for this node 3 to have a child with data 1, you can do that with tree. Evaluate this. There you get a tree where 3 has a child 1, and there are no self loops because these nodes are structurally different nodes in the tree that just happen to have the same data. So that means that options like vertex style that take a vertex name needed to be adapted to work for trees, to work with, instead of vertex names, to work with data. And that's why like vertex style becomes tree element style. And for example, edge shape function becomes parent edge shape function. So yeah, it's kind of a tricky distinction there, but it is important. Moving on to more advanced computations that you can perform on trees. The kind of simplest one of these functions is tree fold. So like we had expression tree that constructs a tree given built-in rules. We also had nest tree that you can give custom rules. So tree fold is the thing that you can give custom rules and have it accumulate the data in a tree. So let's look at an example of that. Here's a tree with multiple levels, and I'm going to use tree fold with these two functions. So this first function here is a binary operation that's applied to the data and the children. The second function here is a function with one argument that is applied to the leaves. So what this is going to do is it's going to wrap the data in each leaf with highlighted. So 2, 4, 5, 6, and 7 will be highlighted. Then the inner nodes 1 and 3 are going to be accumulated together using this binary operation, where basically we'll take the data and have the children as a subscript and have the whole thing be framed. So if we look at this, we see there's the root node. Its subscript is the result of accumulating its children. The first element is this coming from this leaf 2, which has had highlighted applied to it. Similarly, the third element is this leaf 7 that's had highlighted applied to it. And the second element was this subtree here, which has itself been recursively accumulated using this binary operation. Maybe I'll do an even larger tree for fun. So if I do random tree, and fold that tree with the same operators, there we get a little bit more complicated example. So this is kind of the fundamental operation that can be used to implement other functions that accumulate the data in a tree. So here's an example is computing the total of the data in the tree. So this is a function of two arguments. The first argument is the data of the inner node. The second argument is the list of results for the children. So if we take the node, each node, and add it to the total for its children and recursively accumulate the entire tree, what we will get is the sum of all the nodes in a tree in a single depth first traversal. So if we evaluate that, we get 28. Here's a more non-trivial example that further uses the tree structure. So here I've got a family tree. I'm gonna evaluate that. So this is like the family tree of King George II, right? And what I'm interested in is to do a computation that requires not just knowing the data of all of the nodes, but also knowing how these trees are nested. So one property of this tree that fits into that category is computing the parent in this tree who was youngest when they had their first child. So if I wrote some code that basically takes a parent node and the youngest parents from its children and compares them and accumulates that youngest parent to the root node. So we do tree fold of this. And I need to evaluate that code. It's not good. Well, that example got broken. Some more operations available for trees. Tree map and tree scan can apply a function to nodes while traversing a tree. So tree map will take an operator and apply that operator to all the data in the tree. So we do tree map of this, and we get a new tree where F has been applied to all the data. With tree map and tree scan, you can also specify level specifications, much like with the standard Wolfram language functions map and scan. So here's basically how non-negative levels and negative levels work, starting from the root and starting from the leaves respectively. So if I map F on level 2, that should apply F to C, E, and F. If I apply F to level -2, that should apply to these nodes B and F, which are the parents, the immediate parents of leaves. So we evaluate that. And we get this tree, the first case at the non-negative level 2, and the second case at the negative level -2. Some application of tree map, say, if you use the function clustering tree on some random data. So this gives a tree graph with vertex annotations. So if we want to convert this into a tree, we use the function graph tree. So graph tree takes a tree graph and gives a tree object. So there we have the tree object. But now we see one of the differences between graphs and trees is that in graph, each vertex has a unique vertex name. And by default, graph tree gives a tree that uses the vertex names as the data. Now, what I want to do is to take this tree and get this tree. So I want to remove the data for the inner nodes. I don't need these vertex names. right? And also for each leaf here, I want to look up what its label was or what its label should be based on the data. So we could use tree map for this. So if I do tree map applied to this tree, I'm going to look up the annotation that's used in this for the labels is called leaf labels. And for nodes that don't have a label, I want to use the default value none. I'll evaluate this. This will traverse the tree and look up for each node its leaf label, or if there is no leaf label, use none or null. So there we see using tree map to convert the output of graph tree into something that has the same data as this graph has labels. Tree scan, worth mentioning, is a variant of tree map that does not return any result. It just applies the operations. So this is useful when you have side effects. Say if you wanted to walk through this tree and print out the data that you find, you could do tree scan of echo. So we do this, and there we've echoed out the nodes or the data of the nodes of the tree in a depth first order. That brings me to tree traversal order. So this is a way in functions that take level specs to specify what order to actually visit the nodes. So by default, the nodes are visited in a bottom-up depth first order. So here I'm going to start with n equal 1 and just number the nodes of this unlabeled tree, incrementing in each time. So if I do this, I get this tree where the nodes have been numbered starting at 1, and then in a depth first order going 1, 2, 3, 4, 5, 6, and 7. Now in version 13, we added the option tree traversal order to actually specify this. So there's these 3 base orders: depth first, breadth first, and leaves first. So here's an example of breadth first. We do a breadth first traversal. We see the nodes are now labeled 1 to 7, going down the non-negative levels. So we start with 1 and then go 2, 3, next level 4, 5, 6, next level 7. The other nice thing about tree traversal order is that for each base order, you can control whether the traversal goes from top down or bottom up, and similarly, whether it goes from left to right or right to left. Here's an example of that. This is a leaves first traversal that's been modified to go from the top down and from the right to the left. So if we do this, and we start with the root node, that's the furthest node from the leaves. The next furthest node from the leaves is 2. Then the next furthest are the nodes 3 and 4, right, going from right to left. And then finally the leaves going right to left are 5, 6, and 7. In all, this gives 12 possible traversal orders. So this is a table of all the traversal orders for this tree. I'm using the numbers from 1 to 7 for the order that they're visited, but also the same 7 colors for the numbers. So here we can see all the different ways, all the different orders that are available to traverse a tree. Another extension of tree map and tree scan is the ability to supply different elements to the functions. So by default, tree map applies everything to the data. We evaluate this, we see F gets applied to the A, B, C, and D because those are the data of the nodes. Now in version 13.1, we added 11 new elements that can be used, and we can also specify a list of elements. So one example is the element original subtree. So that allows the function to operate on the entire tree. And by giving original subtree, the result of the function doesn't affect the application of other functions. We do tree scan. We see the function f has been applied now to B, C, D, and A, but not just to the data, but to the entire subtree at those nodes. Here's an example of using a list of elements. So this will, rather than applying f to a single argument, we'll apply it to 2 arguments. So we're including the data, but also the index of the node in its list of siblings. So we evaluate this and we see f has been applied to all of the data, a, b, c, d, right? But there's also this second argument now, which is the index. So this is the first sibling. So this is index 1, second sibling as index 2, and so on, index 1, index 2, index 1, index 2, index 3. And the root node doesn't have any siblings, so its index is none. Excuse me. We also have the ability to do pattern matching on the data in a tree. So this is the function tree cases. That is the primary function for extracting subtrees that match, whose data matches a certain pattern. So tree cases of this comma blank question prime q is going to select all of the subtrees whose data is prime. So if we evaluate this, we get these trees, and you can see the data in the root node of each one: 11, 5, 7, 2, 17, 3, 19, and 13 are all of the prime number data in the tree. Just like we have cases, count, and position in the Wolfram language, we also have tree cases, tree count, and tree position. So here's tree count with the same pattern. So this will give the number of nodes that have a prime number as the data, which is just the length of this list, which is 8. So tree count directly computes the length without needing to actually compute the list. Tree position was asked about earlier. Tree position allows you to find the actual position specifications of where that pattern matches. So if I do tree position of this tree, this gives this list of positions. So for example, here, position 1, 1, 1, 3, that corresponds to, so position 1 is this 17 node. Position 1 of that is this 20 node. Position 1 of that is this 15 node. Position 3 of that is this 5 node. So all of these positions here, 1, 1, 1, 1, these are all of the positions where this pattern appears in the tree. So there's a question in chat earlier, what does tree position do when the second argument is blank? So let me show that. So tree position of a tree, comma blank. This simply gives the list of all of the positions in the tree. So these are some of the deeper positions. And then we have things like this at the end. These are like the immediate children. The empty list represents the root node. So this, all of these functions can also take a traversal order option. So if you wanted to list these positions in a different traversal order, you could do that using tree traversal order. So if I say tree traversal order goes to, say, leaves first, there I have the positions of the leaves at the beginning, and then ultimately the root node at the end. So position specs are useful because once you have position specs, you can modify the tree in all different ways at those positions. So one thing you can do with a list of positions is just extract the subtrees at those positions. So here's tree extract, and I'm saying I want the third child. So this will give this subtree with root node containing E and all of its children. So if we do tree extract of that, there we get that tree. Tree extract can also take a list of positions. So this will take the first child of the second child, and the first child of the third child of the third child. So when I evaluate this, get these three nodes, B is the first child, D is the first child of the second child, and I is the first child of the third child of the third child. Just like with extract, you can do independent extractions at consecutive levels. So you could say tree extract of all, comma 2. That will extract the second child from all of the children. So when we do that, we see we get a tree with the same root node, and now its children become the second child of each of its children, right? So this can be used with any tree. In particular, here's an example using XML. So here's that same XML tree, and I'm going to extract 2 is where the body begins. So I want the third element of all of the sales. And so when we do that, there we've extracted all of those subtrees from the XML tree. So you can not only extract the data at those positions, but you can also modify the tree at those positions. So these are the 4 functions for modifying trees at a given position. The first is tree map at. So tree map at is like tree map, except rather than traversing the entire tree, you give the specific positions that you want to apply the function at. So here's those same 3 positions, and we're going to apply the function f at those 3 positions. And we see f has been applied to B, D, and I. We also can modify the tree structure. So we can insert new subtrees. So here I'm going to insert this red leaf as the new second child. So that'll be between f of B and C. When I evaluate that, we see this subtree has been inserted into the tree at the given position. We can entirely replace a subtree at a given position with tree replace part. So this will replace the third child with this blue leaf, Y. So this will replace C and all of its descendants with this leaf. So we do that. There we get this new tree where the third child has been replaced. And finally, tree delete deletes subtrees at the specified positions. So here's the subtree at the 4th position, and all of its children will be deleted. So we do tree delete, and there we go. We've modified that tree. So wrapping things up, in the future, we want to keep expanding on what we've shown here, like XML and JSON. We want to have new structure conversions for things like notebooks and the grammatical text example that I showed. Also things like parse trees for programming languages. We're also interested in more operations related to querying and transforming the tree. So right now you can transform the data of the tree, and you can rewrite trees using tree insert, tree delete, and tree replace part. And we want to really have the ability to use pattern matching and transformation rules to transform tree structures directly. We're also going to keep adding new visualizations and improving the visualizations that we have. And also the end goal of all of this is for trees to be very fast and to be integrated with the Wolfram compiler. So in summary, I've shown how you can represent hierarchical data as trees. I've shown how you can use the Wolfram language trees functionality to construct trees, to visualize trees, and to do all kinds of measurements and computations on trees. So thank you very much. It's been a pleasure to give this talk for the R&D live stream series, and I'll see if there is any further questions in chat. Looks like we're good on questions. All right. So thank you very much. Have a good afternoon or morning, evening, wherever you are in the world.